One of the things I'm kind of fascinated about is this idea of decarbonization. So, as you guys run these big gas turbines, I'm sure you've been looking at carbon capture technologies. What technologies are available today, and what kind of innovations are you guys watching for the future?
So look, I think carbon capture and storage, firstly, let's identify what the naysayers are going to say. What is it? It's scary. It's enabling the longevity of fossil fuels, right? Great points. All great points. And I'll address each of them. So
Today's guest is John Catillaz. He is an energy transition and decarbonization leader at GE Vernova, a global energy technology company with 75,000 employees. GE Vernova's portfolio spans turbines, hydro, nuclear, and more. The company also focuses on decarbonizing existing technologies. Today, roughly 25% of the world's electricity is produced using GE Vernova equipment.
Decarbonization, electricity. As you look across the globe, what do you see?
we're in a multi-speed world. Norway has so much hydro. They're incredibly decarbonized. And compare that to maybe India, South Africa, right, which is still burning quite a significant amount of coal because they don't have a lot of alternatives like natural gas. Their carbon intensity of the grid is going to be significantly higher. And so it's a multi-speed world. So we need to understand that there's countries that are in different trajectories of the energy transition, but the grid, just because you can build it doesn't mean the grid is ready to absorb it and deliver the electrons from point A to point B. In some cases, the grid's not even there. Putting a value on CO2 is one of the most effective tools to incentivize decarbonization or alternatives. But it has to be at a price high enough to warrant that switchover.
When we talk to clients, they'll say we all want to go to zero carbon footprint, but there's not a one size fits all kind of solution. How are we supposed to think about decarbonization of our entire range of operation?
So if you look at how to decarbonize your scope 1 and scope 2 emissions, right, what are the solution sets for that? A few things. First,
Hey, hello everyone. Welcome to Build to Scale. Today we are pleased to have join us John Catillaz, Energy Transition and Decarbonization Leader at GE Vernova. So welcome, John.
thank you. Great to be here.
Please tell us about yourself and your mission at GE Vernova.
Yeah. So I'm going to start with our mission first because people are probably not familiar with GE Vernova, and rightly so. We are a new company, so to speak, coming out of the legacy of what most people do know as General Electric, GE. We still have the same symbol, of course, but GE Vernova was split out of the legacy General Electric April of last year, and we're a standalone, separately traded company altogether with a very purpose-built mission. Now, what is GE Vernova? It is our portfolio of energy technology and capabilities, right? So that means everything from gas turbines and steam turbines, generators, hydro, nuclear, onshore wind and offshore wind, battery storage, as well as a really critical component, which I think we're going to dig into a little bit, Kevin, is electrification systems and the grid and the software that operates on that. So quite frankly, across the energy spectrum, GE Vernova touches just about everything except for maybe solar panels, if you will. And within that portfolio is also ways to decarbonize existing technology. And then, of course, I mentioned nuclear, hydro, wind, producing electricity without emitting CO2 in the first place. So very purpose built around that. We're still a pretty darn big company, around 75,000 employees globally, and we are very much global in nature. Yeah, it's a big guy. Our equipment is around 25% of the electricity that's produced today is from our equipment. So we're a significant player in that realm.
Is this in
And
the
just kind of
US or
globally across the
globally?
globe.
Oh, okay.
Yep. Yep.
Wow.
Yep. Yeah, it's a pretty good size. Now, that has shrunk over time because of these cool things called solar panels. Solar, which we'll get into a little bit, going forward, but it's solar is growing at one of the fastest paces of any energy resource, quite frankly. So, and we expect that to increase. A few other just quick stats, on revenue, we're around a $35 billion revenue business per year, and around 119 billion backlog. And the backlog is an important thing because that's probably something we're going to want to touch on as we kind of explore this, call it, a capacity constrained world, if you will. And the last thing I kind of want to touch on, I think we'll go into it more, is just what we're doing in terms of CapEx. We're in a new environment where we, as a business, are cash flow positive. And while we're returning value to investors, a big portion of what we're doing is CapEx and R&D, right? What are the next advancements in the energy landscape and making sure that we're well positioned, if not leading on those innovations, as well as investing in our own facilities. In fact, yesterday, our CEO just sounded notice that we're going to invest another $41 million into Schenectady, which is where I'm located in New York, to help increase the capacity of the generators that we make and test that go on really large turbines. These are massive machines, but certainly a move in the right direction. Then, yeah, a little bit about me. I think I have one of the coolest jobs. I get to wake up every day and not only just think about the chess pieces of strategy and how we enable our customers to make decisions around their pathways of providing reliable electricity at the lowest cost possible and in a sustainable manner. How do you satisfy all three of those of the classic energy trilemma? And, how do we do that in a sustainable, safe, and reliable way? And a big part of that is these decarbonization trends. I think I'm going to share a few thoughts down the road about the trajectory of electric demand. And in the face of increased electrification, AI, power to X, electric vehicles, how do we provide that power while also taking the existing install base and trying to bring down the carbon intensity, which I define as, the metric tons of CO2 produced per megawatt hour, and continually lower that carbon intensity while satisfying that increased demand in the marketplace. So that's what I get to do every day, and it's an absolute blast, and I'm always learning something new.
Well, okay, I'll lead with carbon intensity because that's really interesting. But before that, maybe you could indulge me just a little bit because your background is not conventional, right? But you didn't grow up as an engineer, but you've worked in power, you've worked in distribution, and now you're working on energy transition and decarbonization. How did that all happen?
Well, you need someone to keep the engineers in check, right? No, it's true. I work in a hallway of engineers, and I'm certainly in the minority. Where it really evolved from is, quite frankly, undergrad, without going into a diatribe on my history. But I took a Energy 101 course in my undergrad coursework, and the light just kind of went off, no pun intended, that like, wow, this energy stuff is a real problem. And I almost, assess it relative to a very addictive drug. Once you get it, you can't live without it. Right? We all need electricity to do our work, to live certain lives of leisure if we're so enabled to, right? And at the same time, we have to do so with really trying to fix the planet and the
Okay.
trajectory that we're on. And so I've always been working in the energy industry, really from the standpoint of the economist, environmental scientist, which is what my background's in.
Fantastic perspective there. So, yeah, so let's jump into it. So,
Sure.
decarbonization, electricity. As you look across the globe, what do you see?
Yeah, so there's a few interesting trends here. We're in a multi-speed world. I think everyone needs to realize that. You know, there's a few great kind of standouts to compare to, and not to pit one country against another. You're doing good, you're bad. It's a function of the natural resources we're on or have access to, right? And a function of our economic growth or current economic status. So looking at two different ends of the spectrum, right? Take our neighbors to the north here, Canada, blessed with significant natural resources, both in the form of water as well as fossil fuels. Their grid today is around 80% decarbonized already, right? Norway is probably the only country out there that can top them. Norway has so much hydro, they're incredibly decarbonized. And compare that to maybe an India, South Africa, right, which is still burning quite a significant amount of coal because they have it. They don't have a lot of alternatives like natural gas, right? Their carbon intensity of the grid is going to be significantly higher, anywhere from 4 to maybe 700 kilograms a megawatt hour. And so it's a multi-speed world. So we need to understand that there's countries that are in different trajectories of the energy transition, different levels of maturity, and different aspirations, quite frankly. And to kind of hammer that point home, there's still 750 million people across the globe. So 750 million people across the globe who don't have access to electricity today.
Hmm, that's right. Yep.
So, right. And, so if you're like in a region like that, you're just trying to get power to your people, right? You're trying to get people out of cooking, with dirty fuels inside that causes poor health, air quality and health issues, things of that nature, to be able to cook with a more sustainable type of fuel or turn a light bulb on so that your children can study at night. I think that's a really interesting trend that should not be forgotten. So there's still a lot of work to do to just turn the lights on and then decarbonize, while more maybe advanced economies where we're fortunate enough to then start focusing on deploying new technology that can further decarbonize what we already have. So that's one, element of what we're seeing. The other thing that's influencing this is I'm going to call it a value on CO2. Putting a value on CO2 is, from a purist economical standpoint, is one of the most effective tools to incentivize decarbonization or alternatives, right? But it has to be at a sustained, predictable price and at a price high enough to warrant that switchover. And so we don't see that in all places. Areas like Canada or Europe, which has the ETS program, we're seeing pretty strong, sustained prices with medium to, in some cases, long-term certainty on price that allow businesses to make decisions that aren't exposed to that type of risk. Other regions, right, like the US is a great example. We don't have a nationwide value on CO2. There's some regional schemes. Asia and other regions also, some of them have mixed values on CO2 that maybe aren't at the price level needed. So kind of plays into that multi-speed world. The other thing, which I find really fascinating, we did an analysis of the pace of growth in demand for electricity. And we asked ourselves, when was the last time we've seen this type of growth? Because for the last many decades, especially in advanced economies, it's been pretty darn flat. And we haven't seen the type of growth in electricity since the post-World War II Reconstruction era. So which is, if you think about how long ago that was, after we built up and enabled the electrification of homes, right? We haven't seen that type of growth since then. And so we're entering that next new phase, which is really exciting. And that comes from some of the stuff we're going to talk about today, these load growth drivers. It comes from the 750 billion people who don't have access, but are starting to get access, every day as we eat into that number. And so I find that trend really important. And, I was actually speaking with someone the other day who had a really interesting thought, which I'm not going to get into the analysis because I haven't done it yet. But they looked at the growth of electricity during the internet boom, essentially, which is
Right.
not to
Yeah.
say it's on par with this AI, but there's certainly some parallels there. And they found some really interesting trends. So I like, for some of your listeners, I think that's food for thought. That's an interesting fundamental change in the way we as humans use technology, right, and depend on it. And that had a pretty good blip in the growth of electricity in the 90s.
Yeah, well, that's a lot to unpack there. I mean, we could spend an hour just talking
Yeah,
about some of those
I
points.
know.
But it's interesting, because of the grid growth, because the IEA and others have been saying that, hey, listen, if we're going to accommodate all of the electrification that we want to have, right, electrification of industries, electric vehicles, AI, data centers, we need about a 4% rate of growth of investment. And as you pointed out, it's been pretty flat for a long time. But I want to come back to this idea of a multi-speed world because the
Yeah.
750 million people is pretty important. And about a year ago, I was part of we were invited to participate in the Columbia University's Center for Global Energy Policy meet. And to your point, it was interesting to see people from Malaysia and Indonesia and India speak and say, listen, all of these things are great that you're talking about, but your coal-fired plants are more than 30 years old. They're fully amortized. We just invested in it 10 years ago. How fast can we actually move in this direction in different regions of the world from your perspective, John?
It's a great point. And there's a lot of facets here. So one of them is obviously the deployment of capital that's needed, as you mentioned, from the deployment of capital to the funding of concrete projects that enable technology suppliers to start manufacturing and building. And it doesn't necessarily stop there because there's not necessarily a missing component, but there's a need to develop the workforce. And here's what I mean by that. If you are one of these big engineering, procurement, construction companies, EPC is the term many folks are familiar with, you are sized to build what's in the pipeline today. So we can build your gas turbine, we can build your wind turbine, but we as a company, we're not the installers. We're not set up for that. It's not what we're good at, right? We're good at, blowing things up and making them spin to create electricity, if you will. And so that's another important part of the supply chain, essentially, that even if we could satisfy the world's demand with all our widgets and gizmos, you still need the workforce out there to install them and keep them running and fix them when they break.
Yeah.
So all those components, I think, need to be considered holistically. Now, in terms of the deployment of the actual technology, The unfortunate answer is, well, it depends. Because coming off of the deployment of the technology is also the most critical and overlooked one. You've mentioned grid a few times, but just because you can build it doesn't mean the grid is ready to absorb
Yep.
it and deliver the electrons from point A to point B. In some cases, the grid's not even there, right? In other cases, the grid is totally at capacity, just like a pipeline. No more room on it. So all those things need to happen in parallel. And to give a few examples of rough timelines, to make this a little more concrete, take an interconnection queue. And what that is, for listeners who aren't aware, you're Mr. Smith in, the Midwest US or wherever, and you call up your utility and say, I am going to build this super clean nuclear power plant. I'm going to let you know I'm going to build it once I can get my interconnection agreement, once you approve that I can interconnect with your grid. Those take anywhere from 5 to 7 years,
Hmm. Yep.
right?
Yep. Okay.
And this is happening in parallel. So they're not necessarily they're all in the critical path per se, but they're not necessarily happening one at a time as discrete projects, if you will. In addition to that, so say you get your interconnection approved, you're going to start building, you've hopefully already placed your order for the equipment. And so for a gas turbine and steam turbine for combined cycle and generator, you could be looking at lead times anywhere from 3 to 5+ years, if you will, from the time you place your order to the time the equipment's on site. Another perhaps 2 years-ish for the EPC to build the plant. Once the all equipment gets there, right, then they have to pour concrete, install it in place, build your smokestacks, your environmental scrubbers, what have you. And then additionally to that, if you're looking, an important thing about the grid and how it interconnects are the substations, these power transformers. And these occur not only at power production centers, but at the actual point of consumption. And probably everyone has driven by these. These are not the little transformers you see in your neighborhood or the gray buckets you see on telephone poles. They look like big drums. These are massive, massive power transformers. You're looking at lead times globally. These are not GE Vernova. This is like industry average, by the way. So it's not just empirical data from us. For power transformers, you're looking at, 4+ year lead times for those. And
Heard about that. Yep.
and they're critical. So if you want to build I don't know, a new, yes, we could say data center, or, a new Mall of America, a huge, huge
Right.
demand center, if you will, you need one of these power transformers to adjust the voltage that's coming off the grid, or to adjust voltage that you're injecting into the grid
Back to
for
grid.
its, long distance transport. So a lot of different things there. And I didn't even get to permitting, right? That's a whole nother thing. And it impacts everything. Even for gas plants or fossil fuel plants, you have air permit requirements, right? In most parts of the world. For wind, you have wind siting and wind permitting, which is incredibly extensive. And, we don't even need to get talking about nuclear, right? We all
Right.
know that is incredibly intensive. If you were to put those all in the critical path, how quickly, if you want to do something tomorrow, I hope you placed your order a while ago, if you will, but that's just the case of a capacity constrained world.
Well, it's interesting because, of course, the big rush to build gigawatt type of data centers, that's kind of top of mind for everybody now. And everybody, what pops into mind is that this will happen tomorrow, which, of course, as you've just eloquently illustrated, is not going to happen. And so a lot can happen between now and 5 to 7 years from now. And it also gets us into this concept of microgrids, which I
Yeah.
actually find very, very, very interesting. But you had mentioned earlier, John, the size and diversity of GE Vernova, and I'm sure you guys have verticalized solutions. But if you were to build, let me ask more of a expansive question. So,
Sure.
if we think about data centers, manufacturing, residential consumers, the mom and pops, I mean, what does a truly holistic solution look like?
Yeah. Yeah. It's a great question. So I would say that those are still forming, but I'll throw out a few different concepts for you. Firstly, if you are a data center, your objective, especially if you're a hyperscaler or, large language or AI based, not maybe your traditional data centers the machine needs to learn. It's a bit of an arms race. You want your machine up and running first, to learn the first, to be the first that's the smartest, that gets used and queried and gets the most value from your paying customers, right? So you want power yesterday if you're doing this. So option one is you do a lot of really interesting analysis on the grid to figure out where could you get interconnected the fastest, has cheap power, that will not wreak havoc on the larger grid. Okay, option one. And there are places that can absorb that, quite frankly. I was with a European customer last month over there, and we were discussing exactly that. They were working with data centers and kind of opening the books on their grid to help them know where they could site them. And it also, to some degree, can help the grid operator, right,
Yeah.
optimize their own grid. So that's option one. Option two, ditch the grid. You mentioned microgrids, right? I'll call it islanded solutions, behind the meter, whatever name you want to slap on it. Build your own power plant that gets you up and running sooner. And when the time comes and the grid's ready, you interconnect with the grid. And with that strategy, there's a few beneficial pathways. One, you're not creating overnight shock on the grid. The grid rather has time to plan, time to be ready to absorb that load as the grid itself builds their own reliability, their own firm capacity. And then when you are ready to interconnect with the grid, you have backup power,
Mhm.
right? And that's an important thing for these data centers, because when you need to offer, 99.999% uptime to your customers, a grid outage is costly. And it happens. It still happens.
Great.
I was looking at some analysis of this index, Kevin, called CAIDI. Have you heard of that?
No, no, please.
Yeah. So CAIDI, CAIDI. It's Customer Average Interruption Duration Index. And it's all utilities track this, but there's really good reporting on it in the US. And since from 2013 to 2023, this average interruption duration index, so hopefully that's pretty transparent, on average, how frequently and how long do our customers lose power, has gone up 3.2% on a CAGR basis,
Wow. Okay.
right? And that includes major events. And I won't get into weatherization necessarily now, but things like, yes, weatherization, increased demand have increased quite frankly, the frequency of these durations driven by, yes, the weather events, but also when I say frequency, I mean it from a voltage perspective.
Right.
When the lights in your house flicker or something like that, those events are becoming more common, leading for these large demand centers like data centers and hyperscalers to almost require their own redundancy so they can stay online.
Right. Well, this is interesting because I think what you just said represents a paradigm shift where the grid itself becomes a backup, and and it's being driven by business models and, of course, AI and data centers. So, with that, I think there's a lot of opportunities for transformation in terms of this holistic solution that one can offer to end customers. And let me bring up the some of the recent events. I
Yeah.
myself am really interested in this idea of behind the meter data because Bloomberg has been highlighting some of this stuff that's happening with Whisker Labs. But basically, it's how is electricity perceived by the end user, and people are starting to see these fluctuations. And here in the U.S., there's an interesting map that was published about how more of these frequency fluctuations are happening the closer you get to a data center. And of course, there was that massive outage in Iberia, which some people blame on the integration or failure to integrate renewables. So, is it data centers? Is it renewables? What do you think is going on there?
It's really both. It's really both. The situation in Iberia, it was unfortunate, right? No one wants to see that happen, and everyone wants to see renewables be champions, in my opinion. Shouldn't say everyone. I'm sure there's some naysayers out there, but
Right, right,
I'm in the go renewables go camp. But that was a result of there being too much renewable capacity on the grid and not enough what we call in the industry firm capacity. And that means actual spinning mechanical machines that are on the grid. Those are needed to protect something called inertia, the inertia of the grid. And when you have weak inertia, poor inertia, that's when you see the lights flicker, right? It's almost like if you were to think about pulling, if you had a yo-yo, but instead of a string, it was a wet piece of spaghetti, right?
all
And
right,
you pull on it and you pull on it a little too hard. That's me and you pulling power. That spaghetti strand just breaks.
right,
And the grid, that spinning yo-yo is what's providing you your power. The grid goes offline, right? It's kind of a crude analogy, but if you essentially have things that are able to continue to spin like a gas powered generator, a nuclear asset, anything that's truly able to spin that is not dependent on weather conditions. That is necessary for the grid to maintain the voltage, the frequency in the system that is required to stop that spaghetti from snapping, essentially. The data centers is kind of an extreme situation of instantaneous power draw. So, if there's anyone out there who's a woodworker or has like a 3-stage motor in their factory, whenever you turn on a table saw, and all of a
Yep.
sudden the lights dim for a quick minute until that saw
You
comes up
get
to
that
speed.
inrush current, right?
You
Yeah.
got it. You got it. And that's essentially what these data centers are using, but on, of course, a much bigger magnitude than your
Right.
than your at-home table saw. And there are certain ways the grid can cope with that, but they need to be installed on the grid. The other thing that needs to occur in many cases are either changes in user behavior or a willingness to have the local utility tell you to change your behavior. And that could be anything from what's called demand side management or other things like maybe we don't turn on the machine at, you know, 12 o'clock on a wicked hot day. Let's just wait
Right.
and batch all our queries and we're going to run them overnight and
Right.
communicate with the grid saying, hey, Mrs. Grid, we're going to run these batches now. Are you ready? And they say yay or nay, right? So it does involve a lot of communication, and you're not literally calling up the grid. It's communication, it's software, it's widgets on the grid that are doing that. The other caveat I do want to say, Kevin, just to return to the renewables discussion in Iberia, there are mechanisms that can enable things like solar and wind, non-purely spinning assets, to help with that voltage regulation, help with the inertia, called synchronous condensers. But essentially creates, a different form of inertia that helps smooth that out. So there are solutions out there, but they're not deployed at scale.
Okay. Okay. All right. So maybe not a fair question, but turbines versus batteries. I mean,
So they got their pluses and minuses. So today, off the shelf, right? Turbines advantage, cheaper, longer duration,
right.
right? Off the shelf battery storage. I'm not going to talk about pumped hydro because pumped hydro does have very long duration, but it's not feasible everywhere, right? So it has its limitations. So if we talk about what we think about battery storage, you know, really around a 4-hour duration today with maybe a pathway to 8 hours. So 8 hours is good, but not necessarily the duration that you need.
Right. Right. Right.
Additionally, a pro for batteries is instantaneous power, right? So if you have an outage at a location, whatever have you, that battery can instantaneously bridge that power through an uninterruptible power supply, UPS it's called, and you're running like barely anything happened. And that's important for data centers. It might be an important advantage for data centers because the load on data centers can go from 0 to 100 miles an hour in microseconds.
Yep.
And batteries are really the only technology out there today that can meet that at that time scale. Turbines are wicked quick, but not like that. They take, you know, 10 minutes for the small ones to come up to full load power, right? Which can seem like an eternity sometimes. So that's a good guy for batteries. The bad guy for batteries, another bad guy would say, like, we need new technology that can wean us off of rare earth materials, especially those that come from conflict zones, right? And that's one. End of life of batteries, right? You got to deal with it properly in a sustainable and environmentally safe way. The other thing is just the size, and it comes down to both size and cost. So, I think Kevin, we were talking about like gigawatt scale, some of these
Yeah.
hyperscalers, right?
Yep.
That's a lot of battery. That's a lot of battery.
Yeah, yeah, yeah. I mean, it's leading to a lot of innovation and experimentation, but I've yet to see kind of mass, scale deployment. Some really interesting stuff, including recycling of heat to create thermal batteries. So that's more
Totally.
circular, right?
Yeah, yeah, exactly.
But when does that actually happen? Because this feeling, as I talk to people in the data center area, that this battle will sort itself out over the next 5 years. I mean, I don't know if that's what you're seeing from your perspective in terms of demand, but for the players in the arena, they don't think it's a 10-year thing.
And just going back to that, was that on just the machine learning timeline or the battery improvement timeline?
Just setting up data centers, getting all of
Yeah.
these hyperscalers out there.
Yeah,
So
I think that's right. I think some might push to the right, but yeah, look, you can build one of these data centers. assuming there's no power, just build the warehouse, right? You can build one of these gigawatt data centers in a year.
Okay.
You
Yep.
know, if you can get your hands on, the chips, right? And that's another thing we didn't even
Yep.
talk about, the supply chain. How fast can the Nvidias of the world, or what have you, call whatever company you want, pump these chips out, and you can get your hands on sufficient ones. But yeah, if you could meet all those, you could have these things built in a year.
Okay. Okay.
Right. So I think you're right with that 5 year, again, maybe it slips to the right, but I agree with that assessment.
Okay. Before we get on to decarbonization, maybe one last question on data centers. So I'm fascinated by some of the IEA data that says, look, in 2020, we were spending about 200 megawatt hours on data centers. Last year was about 413. They're projecting 945 terawatt hours in 2030. So it's roughly doubling every 4 years. Obviously, as one person that we've spoken to says, well, trees don't grow to the sky forever. So there's got to be an end point somewhere. But with respect to things like renewables and gas-fired turbines, what is the proper mix? What do you see? What is the power to X of play here, especially
Yeah.
with respect to grid stability?
I would say anyone who could tell you with an exact science what that mix look like is probably wrong.
Yep.
And whatever I say is probably going to be wrong too, right? We don't know yet. We're still it's not nascent per se. We're in it, right? But we're still figuring it out and working with customers to find the right solution and mix. But at the end of the day, look, I think these data centers, they're not going to run off of 100% wind and solar that is local. From space, it's not feasible. And also just from the uptime and reliability of these assets, right? The wind usually blows at night. We obviously know when the sun's up, when they can operate. So that will be procured from the grid through either PPAs of some sort, or, maybe they actually just buy a project out in Iowa, right? And count that towards the output, they count towards what they consume to offset. So at the end of the day, though, these assets just need firm, reliable power. So a significant amount of that will come from gas. The other part of the equation, I think, to think about, which isn't going to fully answer the question of what's the right mix, but what are the equivalent number of turbines, wind turbines versus a small modular reactor versus a gas turbine versus solar you need to meet that? What did you say, like 400 terawatt hours ish of power, right?
Well, 2030, 945. Yeah. Yeah.
Okay. And so it's a multiplier effect. So you could say, all right, my nuclear small modular reactor can run 8,760 hours a year. That's an entire year. Full bore, run around the clock, and it's 300 megawatts. So let's say I'm building a 300 megawatt machine. I need one of those, right?
All right.
Gas turbines, depending on your size, in combined cycle, you probably need 2 gas turbines with 1 steam turbine behind it to get to the 300. If it's a really big one, it can be just 1 turbine, because we make turbines that are over 300 megawatts. And that can run not as much as a nuclear, because they need to be taken down to
Right.
get
Annual
fixed and have
maintenance.
standard
Yes.
maintenance, just like your car, needs an oil change. It's not going to be on while it's
Right.
getting that oil change, right? Wind, which has a capacity factor of 30%, so it's available to produce electricity at 30%, right? So you need to build 900 megawatts of wind, in theory,
Right.
to equate to the 300 megawatts of nuclear. So yeah, it's carbon free, it's cheap. Solar and wind are cheap. Those costs are coming down every year. So it's a bit of inevitability, and it's going to be part of the mix, but there's no getting around the need for firm capacity for these assets. And then a doubling down of that, I might add, Kevin, is the fact that you need backup,
Right. Yep.
right? So if your 300 megawatt small modular reactor can power you, well, you need 2 as redundant, just in case one of those trips, what have you. But the growth is staggering. It is staggering. So if you look outside the USA, the global growth, you're looking at like 4,000 terawatt hours by, I think I have 2036 in my head,
Okay.
2036. That's the equivalent of adding the consumption of what the US consumes today. So adding to the world a country the size of the United States in just 12 years.
Yeah. Wow. Wow.
Like that sink in. It's like jaw
And that
dropping.
assumes all the interconnects and permitting and all
Yeah,
that other stuff. Right.
totally,
Right. Right.
totally,
Right.
right,
Yep.
right.
Right.
So that's why I also said earlier, like maybe some of this pushes to the right, because are all those ducks going to be in a row in that time frame? Don't know.
That's true. That's true. And One of the things I'm kind of fascinated about is this idea of decarbonization. So, as you guys run these big gas turbines, I'm sure you've been looking at carbon capture technologies. So, let's talk a little bit about that. I mean, what technologies are available today, and what kind of innovations are you guys
Yeah.
watching for the future?
Yeah, no, I love it. Carbon capture is something near and dear to my heart, and it's something I've championed here at GE Vernova for quite some time. So look, I think carbon capture and storage, firstly, let's, just identify what the naysayers are going to say. What is it? It's scary. It's enabling the longevity of fossil fuels, right? Great points. All great points. And I'll address each of them. So carbon capture, what is it? Just like it sounds, it's capturing the CO2 on the back end of any industrial process. It could be
Right.
a cement factory, a steel factory, a power plant. Capturing it and storing it deep underground where it previously was a hydrocarbon, right? An oil molecule or gas molecule in these big caverns underneath where they previously stored safely for millions of years. And there's tons of geology out there to do this. And fun fact, we've been doing it as a human race since the 70s. It's nothing new. We've been doing carbon capture for decades. For a different purpose, it's been used for what's called enhanced oil recovery. We won't get into that, but it's been happening. The chemical that we use today, something off the shelf, if you were to call GE Vernova up and say, I want carbon capture, you got it. The chemical that's used today is called an amine, monoethanolamine. It's its true chemical format. Also nothing new. This has been around since the 20s when we really started harvesting natural gas from the earth to sweeten the gas, make it more combustible, right? And that's kind of the off-the-shelf solution today. And it's a chemical that really just has an affinity, an attraction to CO2. And this stuff rains down the stack, grabs the CO2, and goes into a desorption column, essentially, where the amine is stripped to the CO2 and gets reused and recirculated. And the CO2 gets dried, put into a pipeline where it's going to get shipped and stored. Now, there's about 5,000 miles of pipeline, CO2 pipeline that exists in the world today. Most of it is in the US, most of it in the Southwest, Texas, Colorado, New Mexico. And that's how we've been storing and moving CO2 for the last, 50 years. And so that's off the shelf today. We're working on really the first of a kind in the world as a company in the UK right now called Net Zero Teesside, which will be the first ever natural gas combined cycle power plant with CO2 capture on the back end,
Okay.
which we're working on with partners as well. It's not just a one-man show. I mean, it will capture 95% of the CO2. And that's an important thing to note. Getting to 100% capture is really difficult. It's really difficult without getting through the physics and the chemistry of it. But you would essentially need to build a tower like as tall as the Burj Khalifa, for all of you who know what that is, the
Wow.
big tower in Dubai, to get close to that 100% volume, which is, of course, not realistic. But 95% is pretty damn good. And then what's next? And what can help with the remaining 5%? The next generation of technology is sorbents. Sorbents. Previously it was solvents, so it was a liquid. Sorbents, like think of, when you buy like a new pair of shoes and you got that little moisture packet in there,
Yeah, 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 yeah.
right?
Right.
That's a sorbent. Now that has an affinity to attract water, moisture. The next, we are developing a sorbent-based technology. And what makes that interesting are a few things. One, its application enables the capture plant to be smaller, more efficient. Smaller, more efficiency means lower cost, lower operating cost, lower capex. And it also can be applied to this thing some folks might be familiar with called direct air capture, right?
Right.
And so
Yep.
what I like about DAC, and DAC has a long way to go, don't get me wrong. This is a down the road. We have our own test stand just down the road from me at our corporate R&D facility that's working away. And it looks to me like it's the no regrets solution. Though, like if we were to unwind the clock of all the anthropogenic CO2, since which the clock really started ticking during the Industrial Revolution, right?
Right. Okay.
It's the only way to unwind the clock and try to hit 1.5, or if we hit 3, get back to 1.5, degrees C. You can tell me all day that we can plant trees till you're blue in the face. And as a tree hugger myself, I will say that's not feasible.
Right.
The reason being, if you take one of the utilities in the US, I'm not going to name them, and take 1 year of their CO2 footprint from direct emissions of their power generation facilities, you'd have to plant a forest the size of the state of California and let it grow for 10 years and do that every year,
Right.
right? Now, there are other go out and plant trees by all means. They are good natural CO2 sinks. There's other natural CO2 sinks like the ocean. However, we can't rely on that. So direct air capture with these sorbents is really attractive. And then applying those sorbents to also cement factories, steel factories, power generation is the next step as well. And the other cool thing about direct air capture is you can put it anywhere as long as you have access to the grid.
Right.
It doesn't have to be in your industrial park. You could plop it right over your geologic sequestration site, plug it into the grid, and let it just run away, right?
Right.
Yeah, so I'm really optimistic about carbon capture. Yes, it has its limitations. Yes, we need to figure out how to make it more cost effective. And yes, it won't work everywhere, where maybe your geology is not ideal, or maybe it's just not you don't even have it, the good storage sites. And some regions or countries are going to be like that. But it has the capability to take a pretty big bite out of the future carbon budget, if you will. And I think governments are starting to recognize that. There's certain governments, like take Germany as a great example. If you were to say carbon capture, in Berlin in 2020, you would have been dead on arrival. That message just wouldn't resonate. Look at us where we are now. It's part of their power plant rule. It's allowed now and encouraged. And then the other one for power generation industry, I think is worth touching on because it's in vogue, it's sexy, is hydrogen. You hear about it quite a bit if you're paying attention to the energy space, right? And what's interesting about hydrogen is it's nothing new. It's the easy button. We as a company have been blowing it up for decades in turbines. There's a turbine we have deployed in Asia that has been running on 98% hydrogen blends almost 24/7 for years. So it's nothing new, and it's not even a technology hurdle getting to 100% hydrogen capability. Most turbines can take 5% today. Our biggest turbines can do 50. Some can do 100, and we're developing our pathway so every single turbine we sell can combust 100% hydrogen. The issue isn't blowing it up. The issue is transporting it safely, and the volume that is required. So let me just level set the volume thing first, because I think it's a fascinating statistic. And I'm going to quiz you on this, Kevin. You can get it wrong, but I'm curious to know if you know this. So what is currently the second largest hydrogen storage facility. It used to be the first before they built a big one out in Utah. But the second largest storage facility, where do you think that is?
I would imagine somewhere in APAC.
No, I'll give you a hint. It's out of this world.
Then it's in space. Okay.
It's NASA.
Yes.
That's how we launch everything from Cape Canaveral in Florida into outer space. All those things burn hydrogen. So if you were to plug one of our largest gas turbines in to that storage facility and let it run 100% on hydrogen, how long do you think that supply would last? There's no wrong answer. I'm just curious.
No clue. So
8 hours.
Okay.
Right. So
that's how low the supply chain is, whether it's electrolysis or any other type of mechanism, right?
Yeah, exactly. Electrolysis is a blip on the radar, and that hydrogen today is gray hydrogen. It's produced by cracking CH4 methane, letting the carbon just go out into the air, and that's how we make hydrogen today. That's called gray hydrogen. So yeah, the supply chain and creation of cracking water, H2O, or making blue hydrogen, which is cracking methane, capturing the CO2 and storing it, a little bit cleaner, right? Supply chain is decades and decades and decades away.
Yeah.
And then you got this transport of it, right?
Well, we can say the same thing with CO2. I mean, one of the things that we look at is where is the CO2 being generated? How is it going to be transported? Where is it going to be stored? And then, of course, eventually, how can it be utilized, right?
Yep.
So, so these things are all very interesting. And I did want to touch on something because GE Vernova is a big company solving big problems. But one of the things that when we look at things and when we talk to our clients, here's the following conundrum is here in the US, where there's a lot of really good data about manufacturing, we notice that there's a really long tail to manufacturing. Lots of small sites, lots of medium sites, and then a few super emitters out there. And when we talk to clients, they'll say we have exactly that same profile because of acquisitions made over the years. We have factories that are large, we have factories that are small, some that are medium. We all want to go to zero carbon footprint, but there's not a one size fits all kind of solution of technologies and services. So, how are we supposed to think about decarbonization of our entire range of operations? I don't know if that's something that GE's looked at, but the modular approaches seem to be wanting in this space. And this is something that we're studying a lot here.
Yeah, yeah. No, that's right. So as, a company that makes stuff, we have our own very large manufacturing facilities. One of them is right outside the building I'm in, which is used to be one of the biggest factories in the world. We're looking at internally now. So if you look at how to decarbonize what's known as, right, your scope 1 and scope 2 emissions, right? What are the solution sets for that? A few things. First, you got to find the dogs in the system. Some of the equipment in a lot of these old factories are still analog, right? They're not necessarily the latest and greatest and most efficient. So you have to start there and understanding where the real power suck is. The next phase of things is where you can in your industrial process, electrify it, right? Move away from your dependency on thermal energy and electrify it. So that could look like heat pumps to heat the factory, right? Changing out your arc furnaces, change 2 arc furnaces in your steel smelting and modify a few things to get away from, the Bessemer process, right? So electrify everything you can where you can. And then again, it comes back to, all right, what do I do with, maybe call it the last mile? In some cases, on-site power is going to be a great solution. And that
Right. Okay.
includes cover your rooftop with solar. There's no reason not to, as long as it's structurally sound enough to hold, to
Right.
hold it, of course. Understand what the market looks like for renewable PPAs. Some may scoff at that as, oh, that's taking the easy way out. Yeah, but when doing so, you're really financially purchasing clean electricity that's offsetting something else that, a wind plant is never going to be displaced by a coal plant, right? The coal plant will always be interrupted by a wind asset,
Right.
wherever you make that PPA from. So you're making the carbon intensity of the grid better by doing so, and therefore your own scope 1 and 2 emissions. And in some cases, it's going to be just damn near impossible. There are some industrial processes where fossil fuels, there's no alternative to it to require the thermal energy that's needed in a certain process, or the fossil fuel is essentially needed as a feedstock as well. So it's going to be hard to move away, but it comes down to, there's no one size fits all. It's going to be a mix. Yes, whether it is some carbon capture on your cement plant, electrifying your internal operations, or yes, installing as much solar on your unused sites as you can. It's all of the above, quite frankly, need to be on the table and considered. And the last thing I would also, maybe consider for newer, or, some of your clients who are looking at newer sites for industrialization, firstly, examine the grid and examine the market structures of the grid. And the reason I say market structures is there's certain grids out there that have certain mechanisms in them to ensure that they are getting the cheapest form of power at any given time. And while that's not decarbonization per se, it will, in some case, kind of maximize how they are going to use power and what their buying decisions are, and therefore perhaps drive improvements in efficiency, right, to lower some of those OpEx costs from operating their manufacturing facilities. So kind of a long-winded answer to your question, Kevin, and if it was even an answer, but it's not a
No,
one
it's
size
great.
fits
It's
all.
great.
Yeah.
One last question. One last question.
Sure.
The terms microgrids, I would throw in captive grids and PPAs. And people are asking, okay, well, it's kind of a multi-ball collision between the end user, whether it's a data center or manufacturing, the energy technology providers, right, and including AI as well, and then the utilities. And in that center is this idea of PPAs and modified business models and revenue sharing and all these other things that could happen in the future, especially when you think about using the grid as backup as opposed to primary. I don't know if you have any thoughts on that. That kind of, I guess I'll sneak in a little bit of a sub question underneath that, which is, where do you see microgrids in the future?
I'm going to start with your sub question because that just made a light bulb go off. So microgrids of the future, I think, are going to look very similar to the few, but some solid microgrid examples today. And those are areas of sustained high prices of power and or significant reliability issues. So
Okay.
I'll give a really good point on this one. And it kind of comes full circle to AI because it deals with the manufacturing of chips and microprocessors and all that jazz. So there's a factory that I'm aware of. I'm not going to name names, no reason to. Pretty sizable one of the largest here in the States. And these lithographs that make the chips
Okay.
are incredibly sensitive to fluctuations in the voltage of the grid. And where the grid they're interconnected to, you would look at it and say, gee whiz, this is a very developed part of the world. It's a wealthy part of the world. Grid looks great. Yeah, might have some old infrastructure here and there, but they're doing pretty damn good. What are you telling me? You have voltage problems. These machines are so darn sensitive. Their degree, the degree of freedom they have is hilariously small, 0.00001 in the fluctuation. I'm being dramatic, but that's essentially what it is. And when they fall out of that degree, it causes severe damage to these machines, which aren't cheap. They're millions of dollars a piece. And so as we see things like the CHIPS Act, which is being meant to repatriate, right, the production of chips here in the US, that growing industry, I think, is going to be an attractive one for microgrids. Yeah, I think that's an interesting one to look at. AI, we already kind of discussed behind the meter. That one is really a no-brainer. The difference between the microgrid and I would say a full islanded solution is a good microgrid is going to talk to the greater grid.
Yep. Okay.
Right? It's going to be interconnected. And a good microgrid should be able to not necessarily arbitrage, but optimize what the current power grid is doing and what the price of power it may be versus what itself can deliver to the site. So that's one interesting space on the kind of the lithograph, development of
Yeah, that is
these
very interesting.
chip
It
side of
does tie
things.
everything together quite nicely. And so maybe on that note, we can end here. So,
Sure.
John,
Yep.
thank you very much. It's been a delight. If you'd like to talk more with either FSX or with John, please contact us via our website, futurescalex.com.
Thank you for having me, Kevin. And thank you to FSX for having me as well. Great conversation. I appreciate it.
Thank you.